Okay, welcome. This is Linear Algebra, Maths, Week 10, Tutorial 6, question number 7 onwards. Today is 19th of October 2020. In the last week, we stopped at question 6. I'll now continue with question 7. In this question, we are asked the following. We want to show that the orthogonal projection of a vector y onto a line L through the origin doesn't depend on the vector u. So what is he asking about? First, let me draw the line. Let the line be green color, passing through the origin. This is the line L. I'm just showing a R2 example because that's what he's requesting. So this is the R2 space. Now, he then asks, if we select for ourselves a non-zero vector u on L, so I'm now going to select a blue color u. So this is u. And then I can select another color, maybe deep purple. And this is 2u. And the question is, if I have u and 2u on the line, does it matter if I'm trying to find the projection of y onto u versus the projection of y onto 2u? That's the question. So this is an important question because if you're going to give me a vector u or 2u, does it matter? All right, because you will think that it doesn't matter because both answers should reach this point. That's what we want. And this question is asking you to prove it. All right, to prove it, go to see section 6.2.2, page number 3 and 4. And 6.2.2. Right, we have learned this equation. The projection of vector u on v is this formula. This is u, and this is v, and this point here is the projection of u onto v. And how do we calculate this? Projection of u onto v is u dot v. So u transpose v, as in here, is the same as u dot v. The norm of v square, or if you prefer, sometimes people will write v transpose v. So that's why, because there are so many ways to write the same equation, the students get confused. But you have to learn all these different ways. Just imagine that once you're writing fraction, or you're writing decimal number, or you're writing scientific notation, they all mean the same thing. And then v. So this is the equation. Now, if I am projecting onto 2v, I'm projecting u onto 2v instead of v. So everything else is u dot 2v, 2v, 2v. That's all. So by changing the different vectors, you are just writing a slightly the same equations with a different constant. So we are going to write solving for projection of y. In this case, our problem is y, and then we are projecting on u. But now let us put cu, a constant. This is a constant scalar times the vector u. So therefore, it is equals to y dot cu. So if we want to be pedantic, we'll bracket the cu divided by the norm of cu square times cu. To keep track of what is a scalar, so sometimes we write arrow on top to denote that these are vectors, and the scalars are those without that vectors. Okay, but after a while, if you remember them, then you don't want to write them anymore because it's such a pain. And we have c y dot u because we can bring the constant outside. the dot product, and then we can also, what about this guy? This guy is C square U dot U, and then CU. And then the C's can be collected together, and then they can be divided. And isn't this exactly the same as? And therefore, we prove that it doesn't matter whether you're projecting y onto u, or y onto 2u, or y times any constant of u, the result will land exactly the same place. And that's what you expect anyway. I mean, you're going to say that let us shine a light, and then we shine the light that is perpendicular to the surface we are going to project the vector into. Then the shadow cast by the vector y onto the surface will result in the perpendicular error. And this is the reason why it is called the orthogonal projection, because the error is orthogonal to the surface. Okay, so that's question number 7, and we are done. So the gentleman is telling me this. Yes, you're right. Thank you. Thank you. Now, so to enable learning, what then I provided was this. Okay, so maybe I move this out of the way, and you will see in the tutorial 6 support, this is the perennial problem, right? How to project a vector onto a line. If you like this guy, which is Center for Maths, or this guy, which is Firefly, or this guy, virtually pass, then you'll realize that they are all talking about the same thing. But I guess different people like it to be explained differently. Okay, so that's one. What else we have? And if you have problems with orthogonal and octonormal, some students have that problem. Go and read University College London's write-up. It's very interesting. And the word orthogonality versus octonormality, yeah, so you can listen to him. And octonormal basis O and B, yeah. All right, we'll do all this in this tutorial. Okay, let's do the next one. So this is tutorial 6 support. We've collected a few videos for you to take a look at your free time. Okay. So this is tutorial 6, question 8. Maths, linear algebra. Here, the question is, we want to find not the projection anymore, the distance of y to the subspace W. So y is here, and the subspace W is spanned by 2 vectors. So these 2 guys span, so we have 5 minus 2, 1, 1, 2 minus 1, and the W is spanned by these 2 vectors. So abstractly, what it's asking for is, let us find 2 vectors. Let's call this U1, and let's call this U2. And then now any linear combinations of it forms the space. So this space is W. W is formed by any linear combinations of U1 and U2. Now, later on, you'll realize that our friend Y is not in W. Means that Y is not formed by linear combinations of W. So since this is R2, and it means that our point is not on this R2 plane. And I'm going to say that the point is here. And we call this point Y. Now, if we call this point Y and we want to find the nearest point of Y onto the plane, so this problem is the orthogonal projection. We project here. And therefore, this guy, this is the error of approximating y onto the plane. And this point is the projection of y onto w, the plane. So far, okay? All right, so if you understand up to this point, he says we're interested not in the projection, we're interested in the distance. So this error is the vector. The distance is the norm of the error. Okay, so you have to interpret it to this and then you will get the correct answer. Because if you give us the vector, it is not the distance. All right, so what do we do now? First is, the question is how to find projection of y onto w. So you say that I know how to project y onto a line, but now it is not y on a line, it is y on a plane or on a subspace w. If we look at section 6.2.5, theorem number 8, then we get something. This is the orthogonal decomposition theorem. Go to the sides, 6.2.5, page number 2. And this is exactly the same problem as our tutorial. Basically, we have y, and we want to project y onto the plane w. So this is what I have written down, and he used a shorthand notation called y hat. So this is the typical notations we use. Y hat is the estimate of y. So the hat, we call this the hat, or sometimes called the caret, depending on your choice. So, so this y hat. So how to do that? He says that I'll give you a formula, and the formula looks like this. But the formula comes with a restriction. Restriction is U1 up to UP is called an orthogonal basis of W. So what is an orthogonal basis of W? Right. So let's find out what is basis first. Basis is any independent set of vectors that span W. So you can give me any vectors that spans W, okay. But in addition to that, he needs them to be orthogonal basis. So it means that if I give you vector U1 and vector U2 that spans W, they must be perpendicular to each other. So sometimes I write the perpendicular as a box. Okay. All right. So if you have these two constraints satisfied, U1 to UP are orthogonal basis, then y hat is these equations here. What is this guy? This is projecting. Isn't this exactly projecting y onto the line U1? Yes. And what about this guy? Projecting y onto line UP. So basically, if you have U1 to UP as orthogonal basis, you can project your y one by one onto the axis of the space W. Okay, all right, let's go back and try this. So I have figured this out, and then now I can write the formula. So, but of course, first I have to check, is U1, U2 perpendicular? So how do I check perpendicularity? Is U1 transpose U2? So it is 5 minus 2, 1, multiplied by 1, 2 minus 1, and the answer is 5 minus 4 plus 1, and minus 1, sorry, minus 1, and the answer is 0. So yes, U1 is perpendicular to U2. Therefore, I can employ theorem number which is the projection of y onto w is equals to y dot u1 divided by norm of u1 square u1 plus y dot u2 norm of u2 square u2. Correct? Because there's only u1 and u2. So these are very simple problem. And then you can work it out yourself. And then the answer would be 15 over 30 u1 plus over 6 u2. And the answer is minus 1 minus 8, 4. And this is y hat. Where is y hat in this world? Y hat is this point here. Oh, this is nice. I didn't realize notability allows me to do this. Okay, so this is y hat. What else do I want to do? But what did the question ask for? The question didn't ask for y hat. The question asked for the distance from y to y hat. Means that it's the norm of the error. Therefore, let's find the error first. Error is equals to the vector y minus y hat, right? So this is y minus y hat. Okay, since they are nothing but some vectors, so let's find out what is y is given to us. And we have computed y hats, and the answer is, and now we want to find the norm. Therefore, the distance is the norm, the length. The length is the, we use the Pythagoras theorem, which is the norm of the error. And then it is the square root of this vector. Let's call this vector z, z transpose z. And the answer is 9 plus 36. The answer is square root of 45. And that's the answer. Okay, now I can do question 9. Now, these questions ask us the following. This is theorem 10. So just now I have shown you theorem number 8. And then I want you to compare theorem number 8 with theorem number 10. So first I will go to theorem number 8 first, and then theorem number 10. They are both in the same place, which is 6.2.5, orthogonal decomposition. So they are both, this is the most important section, 6.2.5. Theorem 8 teaches us how to project a vector to a plane given u1, u2, up as orthogonal basis. That's theorem number 8, giving us the equation. Theorem number 10, almost the same thing, except that now the orthogonal basis has changed not to orthogonal basis, but to an octonormal basis. What is orthogonal basis versus octonormal basis? This octonormal basis means that the u's, u1 or ui, the norm, is 1, is equals to 1. All these guys are unit length vectors, but they are perpendicular to each other. That's the word orthogonal. So octonormal is a more special case of orthogonal. Okay, so what's the difference? If you look at this carefully, let's look at the last guy. So it's simple. It's something is missing from theorem 8. So versus theorem 8, the difference is y dot up norm of up square up. This is theorem number 8. Okay. And if I tell you now that the norm of the basis is 1, so the denominator reduces to 1, and then we can cancel away, and therefore that's why we simplify. So theorem 10 is nothing but a simpler form of theorem number 8. Okay, so let's go and see theorem number 8 again. And you see that, okay, this is the last guy. And here, if the UP is unit length, UP is 1. So that's why theorem 8 and theorem 10 are talking about the same thing, except theorem 10 uses orthonormal basis. Clear, guys? All right, so if you are happy with that, then we can go back to the tutorial. And we start. So we say prove theorem 10. U1 to UP are orthonormal basis, and he gives you this theorem 10 equation. Very nice and easy. And now you can figure out, that's why we like orthogonality and we love orthonormality, because it makes our life simpler. So prove this equation. Prove that this equation, number 4, is the same equation as number 5. Wow. Isn't it cool if we can write number 4 as number 5, because it makes our life so much easier? What is number 5? Number 5 collects all the bases as column vectors and put it in U. And then he's saying that UUT times Y will construct the thing above. So that's why we also like matrix algebra, because it makes your very complicated looking formula very simple. Okay. All right, let's try. Let's write equation number 4 first. Projection of Y onto the space W, which is spanned by U1 to UP, that is orthonormal, is Y dot U1, I'm just rewriting this, plus Y dot U. Okay, now, where's the scalar here? These guys are scalars. These are scalar. And scalar in our world now, we're talking about the real number. Later on, if we can get to lecture about week 13, the scalar will become a complex number. All right, but now we still believe that the scalar are just nothing but real number. Now you realize that I have all these scalars, right? I'm going to put them in the vector. I want to write it as, I want to write as y dot u1, y dot u2, y dot up. I want to write it in this form, okay? How? How can I write? Because this is nothing but a p by 1 column vector. But remember, y dot u1, isn't this the same as u1 transpose y, u2 transpose y, and up transpose y? What is u1 transpose? Isn't it u1 transpose equals to column 1 of u transpose? u2 transpose is column 2 of u transpose, and so on. So, isn't this u1 transpose? So I take u1, so I'm going to write your matrix U here, u1, u2, up. And then I'm going to transpose it. So this imply, okay. So this is U transpose matrix. So compare this guy to this guy. So it's very close to this already, right? So all we need to do is put Y here. And then don't we get U1 transpose Y, U2 transpose Y, UP transpose Y. Okay, so I figure out how to get UI transpose Y. So I figure out at least how to get all the scalars. How about these guys? Now, the trick is, of course, to understand that if I have U1 U2, okay, I'm just going to show U1 and U2. X1 and X2, what does this do? Isn't this U1 multiplied by X1 plus U2 multiplied by X2? Yes, it is. So the idea is I'm taking the matrix U multiplying by some column factor to weigh it to get this representation. I compare this guy, this equation which I want, to this weight which I want, and now all I need to do is U1, U2, UP multiplying by the vector U1 transpose Y, U2 transpose Y, UP transpose Y, and I will get the equation I want. And this reduces to U transpose Y equals to the projection of Y onto W. This is U transpose Y, because I can actually manipulate the matrix before the inner product as well. Okay, so this step to this step is that the matrix multiplications is associative. I can do U transpose, then Y multiplied by Y, or I can do, yeah, which is this U times U transpose first, then multiply by Y, or in this case is U multiplied by U transpose times Y first. So, but actually the results are the same, and we prove. So this is theorem number 10. So let me show you where it is. 6.2.5. So theorem number 10. Yep. So the question is asking you to prove this statement below, which is here. All right. If you read it carefully, the answer is already given in the slides. Okay. Question number 10. Answer true, false. So I'll just give the answer first. This is true. Z is orthogonal to W. Sorry, Z is orthogonal to U1, orthogonal to U2. And then this U1 and U2 is used to span the space of W. Then Z must be in the W perp. W perp. W perp is perpendicular to W. Vectors in W perp is perpendicular to vectors in W. There is one exception. Remember that W perp is a subspace. W is a subspace. There is one vector that belongs to these two subspace, and the vector is the zero vector. Zero vector belongs to W. Zero vector belongs to W perp. So then how can zero be? How can this vector which belongs to this guy be perpendicular to W? Because zero is perpendicular to everybody, including himself. Okay, so it doesn't matter. So when I first learned this, then I was very confused because you would think that they are mutually exclusive. That means things belonging to W perp cannot belong to W. But in our case of linear algebra, the zero vectors belong to both of the space because perpendicularity means that the dot product is zero. And since the dot product with zero is zero, therefore this makes sense. It's very strange, but it makes sense. Okay. All right. Now, where would you get the answer? The answer is here. So I'll tell you where to find the answers and please read. So the answer is in 6.2.5, page number 2, the right hand side, the slide. Okay. All right, now we are in B. Each y and subspace W, this is the error vector y minus y hat. Y minus y hat is orthogonal to W, true. By the decomposition theorem, once we have projected y onto W, the residual must be orthogonal to W. Okay, so to see that, again, go to the same page as here. So you realize that 6.2.5 is a very important section. Okay. C. The orthogonal projection of y onto subspace W sometimes depend on the basis of W. So the idea is this. If you have W and W, let's do, I give you U1 and U2, or I give you V1 and V2, or I give you C1 and C2, any basis that spans W. Would the projection y hat, meaning I have a vector here, this is y, and then this is y hat. Would it depend on the basis given to you? And the answer is, of course, not, because it doesn't matter. The basis, when we get linear combinations of it, will span the same space. Doesn't matter what the basis is. Of course, if you give me the wrong basis, it means you only give me, for example, U1 and some combinations of U1. So it is not even a basis, right? Then you can't, then you'll be wrong. But if you give me any basis and any orthogonal, in fact, don't even need to be orthogonal basis. Any basis is fine. Okay. But of course, if the question says in this particular question is talking about orthogonal projection, so you better use the orthogonal basis and use theorem number 8. Okay. D. If Y is a subspace in W, that means this figure, guys. I have a space W. I have a vector Y, and Y is on the plane of W. That's why I say Y is in the W. Yeah. Then orthogonal projection will land exactly on Y, because we have no place to go, right? The nearest point of the orthogonal projection is itself, because Y lives in the subspace. So the answer is yes, true. You can try it. What happens is that when you try it, then the error vector is the zero vector. That's all. Okay. E. If the columns of U is octonormal, so this, the one you see the word octonormal means that all these guys, U1, U2, and here, P of them, UP, and then N, what is N? The size is N element. So this guy put together forms a matrix, and let's call it U. If the columns of the matrix are octonormal, then UTY is orthogonal projection of Y onto U. And yes, that's true, because we have seen it in question number 9. So I think I'm done with question number 10. QR. Okay, QR. QR was confusing to some students, and some students raised some points. So to clarify the points, A and QR. A is decomposed. The word decompose means break down into two matrices such that Q times R equals to A. And then sometimes we say Q is an orthogonal matrix and R is a upper triangle matrix. All right. Now, this wording is correct if A is square. If A is square, for example, if A is n by n, then this guy is n by n, and this guy is n by n, and we're done. Now, so what does orthogonal matrix here means? It means that the columns of Q are octonormal. So it's very strange. We tell you that it's an orthogonal matrix. Then we tell you that the columns are octonormal. What does the octonormal means? Means that the Q1, Q2, up to Qn, the norm of Qi is equals to 1. Qi dotting with Qj when I is not equals to j is 0. The vectors are orthogonal to each other. The norm of the vectors is 1. This is an octonormal basis. Not only is this an octonormal basis, the number of elements is n. The number of columns is n, implying Q transpose Q is equals to I because this is given to us. And something multiplied by something equals to I is the inverse. Therefore, the nicest thing about orthogonal matrix is that the inverse of the orthogonal matrix is transpose, implying Q transpose Q equals to I. All right, so this is why it's a very big deal when we can break a matrix into an orthogonal matrix and upper triangle matrix. We can actually get rid of. So that's why you have AX equals to B, then you say QRX equals to B, and then you say Q transpose QRX equals to Q transpose B, and then this guy wipes out. And then remember, this guy is an upper triangle which looks like this, and therefore we can do the simple back substitution, solving from the back first. However, once in a while, we throw a spanner. What about P? And P is not equals to N. So when that happens, then Q can be an orthogonal matrix or not an orthogonal matrix. So that is the problem. Okay, so where did I explain this? There are two ways or two selection or two, what do you call it, option, whichever you preferred, to perform QR. One is called complete and one is called reduce. If you complete, then Q will be square. If it is reduced, Q will be same size as A. Okay? That's why it's confusing, right? Because there are two ways to select QR. Where have I shared with you this? Okay. So in the supporting material, go to the last few slides. Talk about this is the tutorial 6 support, page number 6. Why is the word orthogonal matrix confusing? And why is there confusion in the word orthogonal for Q? Okay, and the reason is because actually in many books, they'll just tell you Q is orthogonal, and which is true if A is square, which is also true if A is rectangle, if you choose complete QR. Okay, but that's why I used 4 slides to explain this to you, and I wrote a MATLAB code for you to try. You can try this in MATLAB or Python, whichever you prefer. Then if you really want to do QR by yourself, you can see some of these videos. Okay, QR is a very important problem also for us. And then some of you will then realize that there's a new word you might need to use because they'll tell you Q is not an orthogonal matrix. Instead, they give you a new word, which is called a unitary matrix. And the reason why they would use the word unitary is because unitary is for complex Q. Okay, and for real Q, we just call it orthogonal. If Q is complex, then we call it unitary. All right. Now, so I cannot finish question 11. What I'm going to do is instead, I will take some time to record this and put it up. But in fact, I have already given you some of these hints for you to read by yourself. So before I end, uh, maybe I'll give you some tips to study in for this course. The first tip is this: you definitely have to watch the videos before attempting the tutorials. That's one. Two is that you should attempt the tutorials before you come, so that maybe you'll get a different insight to how I explained for this. If you just come and listen, then maybe you get only about 25% or 50% of what I'm saying. But if you have tried it and come, then maybe you can reach up to 80 to 90%. That's one. If you only understand the lectures, trying to do the tutorial, there is still a huge gap. Okay. So understanding the lectures doesn't mean understanding how to do the tutorials. There's a huge gap, or the lab. And the last thing is my lecture slides. Some of the students complain that it is too wordy. Okay, it is wordy because I'm trying to replace a book. In the university, you should be using books. You should be reading textbooks and studying it. And of course, there are lots of online videos now. But if you're only studying from notes, even up to year 2 or year 3, then something is a little bit off. Because if you're only getting the important points given to you, then you will realize that many things are missing. Of course, you can, in fact, given that my notes are verbose, you can actually generate your own sets of notes, short notes. In the past, we allow the student to bring in one page of cheat sheet. So the cheat sheet is a very nice way to summarize all you have learned. But this time we are not going to allow you to use any cheat sheet and things like that. So this Thursday's quiz, all you can do is learn how to do all the tutorials and you memorize a few of these theorems. Vinay, yeah.
Yeah, Prof, there's some questions in the chat.
If Q is not a square, how can it be orthogonal? $1 million question, right? So when Q is not square, it is not orthogonal. So how to do it orthogonal? So you realize that you can still use QR decomposition, and in my tutorial 6 support here, if you wish to implement your QR decomposition on A, which is not square, how do you do it? Instead of throwing A into the Gram-Schmidt, you throw A and A tilde. And A tilde is, for example, identity. And then basically you're throwing more columns into the Gram-Schmidt and you are stopping at when you're done. This is how to answer your question. If Q is not square, it is not orthogonal. But it can be, but for tall A, we can still modify our Gram-Schmidt to make it orthogonal. That's the confusion. Brandon, U times U transpose is identity. Yes, if U is square. 10C. The question is, projecting Y onto subspace W gives you Y hat. And he says, sometimes depending on the basis. Now, if this is W, so if this is W, I can create W by giving you different bases, U1 and U2, right? Or I can give you V1 and V2. Doesn't matter, okay? And as long as they're orthogonal, in fact, even if they're not orthogonal, it's fine. If once I've given you a basis, I have given you the space of W. And whichever basis I give you, if I ask you to project this guy, he will land exactly the same space. Y hat will always be on W, regardless of which basis I give you. Okay? So that's the answer. So it does not depend.